pool would be discounted. So but it's kind of within, yeah, once you get them, but you have to also have experience doing that kind of stuff. So if you want like 10 years of experience in LinkedIn, so.
All right, it's time for us to get started. How'd the exam go?
I felt good.
So I think grading for that is just starting now. I handed them off to Hunter, so hopefully they get graded and turned around in the next couple days. You should also be getting, for those of you who took the 8th, you should be getting your results today. We ended up with a 65.2% pass rate this quarter, which is about 16% better than it's been either fall or winter of this year. So very excited to see that. I plan to do a lot more analysis into exactly how that went with the hope of changing up some curriculum and making sure that I'm doing the best that I can to help prepare people for it. I pushed back the homework due date from tonight to Wednesday on Friday. So you have a couple extra days, although I may be finding the next thing in the meantime, since we have now gone over caching, we've gone over, we're finishing up merge sort, and we're going to be tackling quick sort here in short order. So there's a good amount of that we still need to get some practice with as we continue to move forward. So today's task is going to be to live code merge sort to make sure that that is hopefully intuitively down, and it'll be code down by the end of the day, and we'll start tackling quick sort. And then the rest of this week, we're going to be talking about trees, which is an incredibly important data structure in computer science. So that is the plan. Questions or concerns before we start coding merge sort? Yeah.
Did we ever go over how to like code the infix and postfix for our home system
We did not, but I guess there was pseudocode
on the slides?
yeah, let's see, what have I, it's been a while since we did this. So your reference should be. Should be down with the stacks, I guess there's stacks. So we have postfix, and then we said, how could we use a stack to solve postfix expressions? This is the pseudocode that you'll want to use for that, embedded on the slide. And then we went over this as well. So the infix to postfix conversion, we have the pseudocode on the left and then the example on the right. So I would use these slides as we're putting this together. Trying to use that pseudocode to turn that into actual code. And those slides should be up because that was part of what was on the exam. So I think those are up. All right, back in advanced sorts, we are going to go code us up some merge sort. So who can give me a large scale overview of what is merge sort? How does it work?
Split the array and then we do it on the side.
Yeah, so we're doing a recursive setup where we have an array, we're going to split it into a left-hand side and a right-hand side, and then we're going to recursively call merge sort on the left-hand side and the right-hand side. Once we are done with that, we need to go through this merge procedure of filling a new array with the sorted left and right halves, because once we return from those recursive calls, the left-hand side and the right-hand side are sorted. And so we just need to take the going from smallest value to largest value, compare them, and fill up the array. So let's actually go through that process of coding up the merge sort and merge procedure as we go through that. So I think the place to start is with merge sort. We're gonna make a separate procedure for merge, just because that's relatively complicated. And it's good in the big picture to break things down into their relative components. We don't want to make a procedure that's longer than the screen, really. Because then you have a lot of explaining to do for what is all going on in this, so. We're gonna call this merge sort. And a merge sort is going to take the array that we want to sort. We can call this whatever we want. Does anyone have a preference beyond ARR or R array, very pirate themed array? We can call it whatever we want, but we want to split it up into a left-hand side and a right-hand side, so we need some way to break that tie if it's odd, if it has an odd length. How are we going to do this, and or how are we going to determine if we are in the base case? Yeah, so we would say something like, if the length of the array is, I guess we could technically end up somehow with a 0, so let's just say less than or equal to 1. Just to catch that off case, then we're done and we can return, because an array of length 0 or an array of length 1 is already sorted. So that's our base case. Just need to check the length of the passed in array. Great. If that's not the case, then we're in the recursive case. If we're in the recursive case, we need to do that breaking down into the left-hand side and the right-hand side. So that means we need to figure out where the midpoint is. How are we going to figure out where the midpoint is? Sounds good to me. So is that going to be good enough? What happens if it's odd? It breaks the tie for us with interdivision. Let's say the length of the array is 9. This would say that the midpoint is 4, which is a valid index to be the middle. It means we would have 0, 1, 2, 3, 4, 5, 6, 7, 8. So we have one of length 5 and one of length 4, which works. So I like this. We don't want to make this +1, because if we did that and then divide it by 2, we would end up with, rather than 5 and 4, we'd end up with 6 and 3. So I think this works nicely. If the array were at length 8, we would also get 4. So we'd have, so I think we want to stop before we reach that point. 0, 1, 2, 3 is going to be half. So going up to but not including this mid. And then we would have 4, 5, 6, 7 as the second half. So going up to but not including index mid is going to be the left half. And starting at mid and going up to the end is going to be the right half. This is just something that is worth considering. When you find that midpoint, take a moment, take a step back and say, what does that mean in terms of an array index? Does it work for an odd length array? Does it work for an even length array? I'm doing this in place of writing unit tests for this, but you would absolutely want to have some unit tests to make sure that this is actually splitting it in half. So we need to pass in some kind of array into the lower part of this and into the upper part of this. What becomes difficult is there a way to do this without breaking this down into new structures?
Without taking like 2 new arrays.
Yeah. The easy solution is going to be to make new arrays. There's not really anything horribly wrong with that, as long as we make the appropriate number of recursive calls. So we know that merge sort ideally is supposed to be an n log n algorithm. That means that we want to make sure that we have log n calls and that the complexity of each one of those calls is linear. We already know that once we return from that recursive depth, that the merge procedure is linear. What that tells us is we have anything that is linear in nature we can do here without really affecting the runtime order. So if we wanted to make new arrays and fill those new arrays, those are going to be 2 linear time operations, which is okay, because merge at this level is also going to be linear. So we will not be affecting the running time by making a decision to do something at this stage that is linear. So we're going to do that. We're going to say, we're going to make a left half. And we're going to make it of size mid. So index 0 up to index mid -1, that's going to be that. Then we're going to make a right. We can't say mid here because then both of these would be the same size, which wouldn't work if we had an odd sized array. So how do we get everything other than mid? How do we make this the appropriate size? Yeah, n minus mid. So if n was 9, and by n here, of course, we the length of the array. Since we're seeing this happen quite a few times, maybe it's worth making something that stores it. And now we can, rather than have something that is long, we can just call this n. Makes things a little bit cleaner. So now we need to fill the left and right. How could we write some code to fill the left? We could do an array copy, absolutely. How can we write that as a loop? We want straight less than mid, if we do less than or equal to mid, so we said we wanted to come up to but not include the mid index. So if we do this, then what is the guts of that loop? They are great. So this is the exact loop that an array copy would get for you. I'm just demoing it because it's nice to have the tools to be able to do that, but it's also nice to know exactly how that works. So we would pass index 0 and then say we're going to copy from 0 up to but not including mid from position I in the destination and up to position I in the source. So that will fill left. Now we need to fill right. This one's a little bit trickier. First of all, can I reuse I? Yeah. Yes, we can, because they're sequential loops. What is I going to start out at? Mid. What is next? Less than or equal to? Yes. What are the guts of this loop? Right, I are. What? Right at, do we want to start out at mid? In our destination array? We want to start at index 0 in our destination array. So what goes inside of here in order to get that? Yeah, I minus mid. This will say, so if we start I out at mid, the very first time around, this is mid minus mid, which is 0. Then when I becomes mid plus 1 minus mid becomes 1. So I minus mid is exactly what we want here. What's the source? Since I is not starting out at 0, I is starting out at mid, the first thing we copy is the mid value in the source array to I minus mid in the destination, which is going to bring it back to the beginning. So we're going to be saying the second half of the source is the entirety of the destination, since the destination is about half the size of the original. So I buy it. I think this will work. It's already starting to get a little bit long, but we don't have much left to do here, I don't think. So what comes next? Do recursive calls. What do those look like? Want to call merge sort, and we want to pass it the left half, the new array. We want to call merge sort on the right half. Note that when those return, since we're passing these by reference, we don't need to store any results. It's just going to modify left and right to eventually sort those. Great. We also now need to merge the results together, and rather than write all of the logic for that, I'm going to have a separate, something separate for that. So we're going to call merge. What is merge going to require? What parameters? What do we need in order to merge them?
Arrays.
The left and right arrays. What else? Either merge needs to return something, or it needs to modify the original array to be able to have the sorted final array there. So I think we're going to do that. We're going to pass in the original array, the left half, and the right half. And the idea is that by the end of merge, rather than returning something when we don't need to, we're going to take the sorted left, the sorted right, and we're going to arrange that into a sorted ARR, which we can then return from here. And we use the same reference variable that we did and don't need to reassign. So that will be the goal. So this is the merge sort algorithm. Finish it off, we just need to write merge. So this is a public static void. It's going to take an int array that we're going to call the original array that we're going to fill out. It's going to take left, and it's going to take right. Great. Just like before, it's probably true that we're going to be using these lengths. So maybe we should store these off in values of some kind. We'll see. We'll see if we end up using it enough to want to refactor it to do that. So how are we going to merge this? What assumptions, what valid assumptions can we make here? Yeah. You can assume that left and right are sorted.
You can't find like you just pick one of them. You find starting one value and it's right to kind of like a selection.
Yeah. Yeah. So let's, we could use probably. Let's set these to be 0 right off the bat. So this is going to be the current position into the left and right that are going to start out at 0, saying we're pointing at the original 0 index. And as we find something that we're going to write to the array, Let's also make a current position into the array. How do we want to do this?
First index.
Yeah, I want to check those indices. What's our termination condition? Because I think this is basically a loop, right? We want to continue to do this. What's our termination condition? We want to continue to look at left of cur left and right of cur right until what?
I think we've reached the end of both left and right for current arrays built.
Yeah, I think we want some special logic after the fact for what happens when we fall off the end of one of them. But as long as we haven't fallen off either one, then the logic's gonna stay the same. So let's just basically say, while her left is less than left dot length, and her right is less than right dot length. This says we haven't fallen off the end of either array. As long as we haven't done that, we know there's something that we can point to in either one, which means there's something to compare. We need to figure out now which one of those elements is smaller. So we can use a conditional to determine which one of those is smaller. If left of her left is less than right of her right, then we know that the left is the smaller one. If there's a tie, this will just be broken, so it doesn't really matter if you put less than or equal to here. Sure, we'll break the tie by saying this comes from the left. One of them needs to be, you can either put that there or not, shouldn't affect the result. Then we want ARR of the current position in that array to get the one from the left, because the left one is smaller. So left of her left. When we do this, we probably need to change the pointers to point to the associated next things. So we want to point to the next thing in ARR and the next thing in left. So we want the current pointers. So cur left should bump up and cur ARR should bump up. We will find that we can factor this out momentarily. If that's not the case, you don't need an extra condition here. If it's not, if the smaller value doesn't come from the left, then it must come from the right. So the issue here is we have the same line in both our if and our else. That tells us we can factor this out. So I'm actually going to do that. We're going to get rid of it here, and we're going to get rid of it here. And we're going to do it in preparation of the pass. This just makes our code ever so slightly shorter. Once we do it regardless of the if or the else, we can factor it out. Just make sure that you put it in the appropriate place. We want to make sure we do it before we loop back around. Any IDE will do this. If you put your cursor at the end of a block, it will highlight what that block is associated with. You can also just look up and see that, sure enough, we want to do this before we loop back around our while. So I think this logic is good for the base case of our merge, the basic case. I shouldn't call it a base case because it's not recursive, but the basic case of we haven't fallen off the end of one of our arrays. How could we handle the fact that we might have fallen off of one but not the other now? Is there an elegant way to do that? what's going to be true if we still have elements left to copy from our left? We can't have both the left and the right, because then we'd still be in this case. So either we're done. We have some elements from the original left to copy still, or we have elements that were from the original right to copy still. Does that make sense?
Either half of that and when the while loop is still true.
Yeah. So we can phrase this as sequential loops to say basically, while her left is less than left dot length, this will just straight up be false the first time around if we didn't fall off the end of the right with some additional things to do in the left. So this will only trigger if there is stuff left to do in the original left part of the array. So we can now just basically take this, copy it, and bump up our associated pointers. This will continue this logic. Then we can do exactly the same thing for the right half. Because if this were false, then we're just not going to do that associated logic, but we should still check the right-hand side. So we can say while her right is less than right dot length, then we borrow this logic and that logic. And I buy that this is the entire merge procedure. What do we think? We agree? Are there any flaws with this associated logic? Tested it out, it works. I would still like to test it just to be absolutely sure. If we wanted to write some kind of main that uses this, we make an int array. Name it something. Doesn't matter. We'll pass it some stuff. Get out some integers. What? There. 1,000. One. Good enough.
-2,
22, did I hear that too?
-2.
-2. Love it. All right, so then we want to call merge sort, which we'll call merge. Then we could print arrays dot toString, the int array, actually it's better which one of these you pick, ARR. And we should see that it's sorted. And it is. So I think this logic is reasonable. Does anyone have any questions about what we put together? How we put it together? The logic of putting it together? How you think of any of these things? I just kind of dove in, which is not really there should be some planning associated with it, but. So we have a merge sort procedure that does the breaking down into its cases. We sort the left and the right half. And then we merge it together, and we did that recursively, very similarly to how we did on the board. The only thing that was left to do was to go through the merge procedure once we are done with those recursive calls. And merge, just make sure, given a sorted left half and right half. That we merge it together into one associated, the original associated array, unsorted. And that can become the new left-hand side or the new right-hand side for some parent problem. Since this is recursive in nature. You came up with that base case and a recursive case, so it doesn't matter how long the original array is. We just make sure that we break it down appropriately and put it back together appropriately. How do we feel about merge sort? Do we feel like we intuitively understand it? Do we intuitively understand the code behind it? If you're on the mid side of this, then I would love to see you during office hours to just kind of talk it through. See how it is that you understand it, walk through this code line by line. If that would be useful to you, I'd love to see you. All right, we are going to introduce the next good sort. I guess we talked about the complexity while we put it together. People feel like they have a good intuitive understanding of the complexity and why it is n log n. Let's go over it, because I think that would be good. So we had these two components. We had the preparation for breaking it down. Let's actually just go back and look at the code. I feel like that will help. So we need to figure out the complexity of merge sort, and we need to figure out the complexity of merge. So since we are making new arrays and copying them over here, that is linear in nature. That's going to depend on the length of the original array, ARR. So what is the associated complexity of that plus the merge? Because that's basically, if we ignore these recursive calls and say these never happen, then we have sequential linear tasks. We're breaking things down into a left-hand side and a right-hand side. That's involving a linear time copy. And then the merge procedure is going to go through and say for each element in the new sorted array, it's either going to come from the left half or the right half. So that's also linear. Since we're filling up something of size n and it's going to take a constant amount of time, does that come from the left or right? It comes from the left. Does that come from the left or right? It comes from the right. There's a linear amount of work there. It's constant for each element of the array, since you're asking the same question over and over and over. The time it takes to fill each one of those bins is at most 2 questions. It's either this question and this amount of work, or it is the other question and a constant amount of work, which we will do for each element in ARR. So it doesn't really matter that there are 3 sequential loops here. We can analyze all 3 of those loops together and say the purpose of all 3 of these loops is to fill every bin in ARR. How long is ARR? Well, it's the length of the original array. We're going to be doing this some number of times for some number of recursive calls. So let's say we have an array of size 8 to start with. So we would agree that this amount of work is n, where in this case n is 8. When we break this down into a left-hand side and a right-hand side, we're going to be solving, again, n things. If we look at combined, how much work is it to fill out the left-hand side plus the right-hand side? That's another n amount of work. And we're going to break these down into a left-hand side and a right-hand side. That's another n amount of work. And we're gonna break each one of these down. And that's another n work. So the question is, how many n's are there? And how does that scale with the size of n? So we said in this case, n equals 8. How many more layers would there be here if n were 16 instead of 8? Would not be double. A good guess. It's just one more. Yeah, this would be the left-hand side of the n equals 16. And there would be another right-hand side associated with it. So if n is 16, there would just be one more layer of work to do. If n were 32, there'd be one more layer of work to do. If n were 64, one more layer of work to do. So we double the size of the array and we add 1 to the recursive depth. What's happening at each one of these recursive depths? Some amount of work proportional to the size. So it's linear for each depth. The question is how many depths? How much depth do we have here? And it's proportional to the log of the array size. So we have a linear time procedure that we're going to be doing a logarithmic number of times. Since that's kind of a loop inside of a loop, then what we have is an n log n procedure. Log n times for doing something with work proportional to n. This scales significantly faster than n squared. If you want to see what that looks like, pick out something like some power of 2 that's close to 1,000, 1024. If we wanted to square 1024, what do you get approximately?
Like 4,000.
So it's close to 1,000-ish. What's 1,000 times 1,000? Million? So if we did one of our quadratic sorts, we would have an amount of work to do proportional to 1,000,000 things. There'd be 1,000,000 comparisons, swaps, and again, it's proportional to. Whether it's 2 times or 4 times, it doesn't matter as long as it scales in such a way that it's proportional to 1,000,000. What about n times the log of n? So what is 1024 times the log base 2 of 1024? So again, this is just about 1,000. What's the log of 1,000? Log base 2 of 1,000. 2 to what power is 1024? 10. So what's 1,000 times 10? 10,000? 10,000 is what percent of 1,000,000? 1%. So using merge sort will be approximately 1% of the work as bubble sort or selection sort or insertion sort for a problem of size 1,000. This difference gets bigger and bigger and bigger the larger the array gets. So if you wanted to do this with 1,000,000 instead of 1,000, 1,000,000 squared is what? What's 1,000,000 times 1,000,000? Yeah, 1,000,000 squared is 1,000,000,000,000. And again, these are, not exactly 1,000,000, but we have about 1,000,000,000,000. What is log base 2 of 1,000,000?
So log of a million is actually 20. It's twice as much as it was here, even though we multiplied this by 1,000. So 1 million times 20 is about 20 million. What is 20 million as a percentage of 1 trillion? It's 1/50,000. So merge sort will be something like 50,000 times faster than selection sort for an array of size 1 million. Which is a little crazy to think about. So as this scales in size, the merge sort is just going to get better and better and better proportionally to the other sorts that we've looked at. So as easy as it was to implement the other sorts, the sort that we just looked at is significantly faster. And this is what should be used if you don't know if the size of the array is going to be under 1,000. Because even if you can do 1 billion operations per second, that's a lot of operations per second. How long will it take to do 1 trillion operations if you can do 1 billion operations per second? Thousand seconds? How long is 1,000 seconds? Yeah, just about 1/4 of an hour. A little over 1/4 of an hour, so it's something between 15 and 20 minutes, probably closer to 20 minutes. So if you want your sort to take 20 minutes for 1 million elements, use one of those basic sorts. How long will it take to do 20 billion operations if you can do 1 billion operations per second? It's done. It's done before you can start and stop a stopwatch. I don't know if anyone else tried to do this as a kid. I don't know why I tried to do this. It was the start and stop a stopwatch challenge. How fast can you start it and stop it? For the life of me, I could not get under 600ths of a second. I could consistently hit 600ths of a second, but I could not hit 5. This is faster than that. It's done before you can start and stop a stopwatch versus 20 minutes. And that's going to be the difference between a very happy client and a very angry client. Why does this take 20 minutes when it doesn't need to? So that's just the math behind why this is efficient and works the way that it does. All right, time to introduce our next algorithm. Any other questions on anything that we just covered? All right, let's introduce quicksort. Apparently I didn't animate this. That is perfectly fine. We're gone. So, just like before, we have an array of random integers that's not sorted. What we're going to do is we're going to pick a random pivot value. And for this, we're just going to use the last element of the array. And we're going to say, whatever you happen to be, we're going to now determine what of the existing array is larger than that value and smaller than that value. We're going to make a pass through the array, and everything that is smaller than that value is going to go on the left. Everything that is larger than that value is going to go on the right. Once we've identified where it is, such that everything to the left of that part of the array is less than the pivot value, everything that is greater than that pivot value is on the right part of the array, we're going to swap the pivot into place. What we know at that point is that in the final sorted list, the pivot is right where it needs to be. The left-hand side of the array is unsorted, but less than the pivot. The right-hand side of the array is unsorted, but greater than the pivot, but the pivot is right where it belongs in the sorted list. We then recurse on the left-hand side and the right-hand side. So rather than recursing and saying, we'll figure it out when you come back up, we're doing a lot of the work in advance. And then when we recurse, once we're done recursing, the list is sorted. So when we talked about tail recursion, quicksort is tail recursive. Merge sort is not. Which is why Java, which doesn't support tail recursion, uses merge sort. And a language like C++ that does support tail recursion uses quicksort. And that's because we talked about the levels, the number of levels of recursion here. There's no guarantee that merge sort will work at a depth more than about 40. Granted, since this is exponential scaling, a recursive depth of size 40 is a massive array that we have no reason to try to sort in practice. But quicksort scales in that way, which is why some languages use quicksort, because this is also an n log n algorithm. Even though it seems like it's going to be less efficient than merge sort as we go get an example of it. So how are we actually going to go about this process? We want to kind of, I'll give you a basic example. I don't have time to draw this out, but let's say we have we'll just talk about it in general. So if we have an array of size 8, I just like powers of 2, they're nice. We're going to pick the pivot value. The pivot value is just going to be this last element. The idea is, whatever this value happens to be, we want to make sure that everything less than this value ends up over here, everything greater than this value ends up over here. And when we're done with this, we're going to swap this into its associated place, wherever that happens to be. Ideally, that's somewhere close to the middle. But it might not be. This might be the minimum element, in which case we're just going to swap it in place at the beginning of the array once we're done with it. But if this is somewhere in the middle, then eventually this may end up here, where everything greater than that is over here, everything less than that is over here. We know that this spot is now finalized, so we can do a recursive call on this left half and this right half without this. So the right half is here and the left half is here. We don't include the sorted pivot value in that call because it's already in place. You don't need to worry about it. So we're going to ignore this, recurse on the left-hand side and the right-hand side. This is just everything less than the original pivot, greater than the original pivot. By the time we reach the bottom of that recursion where all of our arrays are of size 1, the original array is sorted. So we do this on the original array's indices. Are there any questions about the basic idea of quicksort? When we recursively call this, when we have the left-hand side, then this is going to be the new pivot. And the right-hand side, this is going to be the new pivot. Because they're the rightmost elements of these subproblems, the left-hand side and the right-hand side. So tomorrow we will come back and we'll do a full board example, looking at exactly how this is going to work. And then we're going to put it up. If anyone has any questions about the current assignments, I will have office hours starting now. Yeah. I can figure out how to reset this.
That means, yeah. And then, how was it, did you read it? No?
Has not been graded, it was just. So hopefully the next couple of days. Yeah, in the winter and spring of next year. Oh, no, C#. Okay, I'm doing Unity. If I have to go, I should be perfectly fine. It's very syntactically simple, and then it'll also introduce you to C#. Yeah, no series required. Kind of stuff will be covered. So 2-course sequence. The first course is going to be a lot of game design principles. and a lot of learning Unit and learning C#. The second course in that is all application. So you'll be making games in small teams, you'll be reviewing each other's games. So I take a very hands-on approach to that. I don't know what's fun and what's, rather, I know what's fun and what's not for me, but not in general. So you're making games for people in the rest of the class. You'll get 4 or 5 games at the end of each of these, so make 3 of them over the course of 10 weeks. And then you will be receiving reviews / feedback, and I grade the quality of the reviews. So basically, everyone else will have to talk about the game design principles in order to get full credit for the reviews, but then I let the quality of basically whatever scores people give the game stands as the grade of the game. And then about a fourth of your class will play each game ideally. So you'll get something like 11 or 12 reviews averaged, and of course, people then have the right or the ability to say, I don't think this review was fair, given something, and then I can take that out of the grade portion of it. People really don't like that, but then you get anonymized feedback, and you get 11 or 12 reviews of the game that you made. Then you work in a completely different team the next time around. So you bring the code that you wrote from your first game, and someone else brings the code that they wrote from their next game, and someone else brings the code that they wrote from their next game, and then you have 3 or 4 weeks to put together the next game, given the experience that you all have developing all of the past code. I'm working with the design department to do things like you can request assets and they'll make assets for you. So I think that would be really cool. Yeah. Cool. So, yeah, that's the idea behind the learn about the principles, learn about C# communities in part 1, and you apply and have things that you can put on GitHub. Very cool for us, the second part. Cool, sounds good. Yeah, thank you.